Let's do share screen. Let's do the usual stuff here. Share. All right, here we go. So I recently moved into the 20th century and got rid of my old flip phone and got an iPhone. And so I'm finding that using the iPhone is helping me learn how to use the iPad, because they're similar enough, you know, swiping things this way and that. Yeah. So now I'm chained to my iPhone like everybody else in the universe. I have to charge it every night. All my two-factor authentication is tied to it. So if I lose my phone, I'm in trouble, all that stuff.
I think half the space on my phone is authentication apps at this point.
Authentication apps, yeah. Well, one negative of an iPhone, you know, compared to these older phones, the same would apply for an Android, is that they track you everywhere, and you know, you can only partially remove that. So I think it's probably true that in the United States this is mostly used for commercial purposes, but I'm not sure it's totally used for that. Anyway, it certainly is. There's a potential for abuse. Okay, get a little turnout here tonight. I'm going to do that. No, let's see. What do I want to do? I want to do that. Do that.
I had a question, actually.
Yeah. Okay.
Do you know when the video for the last lecture will?
Oh yeah. So I just been negligent in getting that up. I can do it tomorrow morning. I will do it tomorrow morning because I got to get both of them up.
No worries. Thanks. I just couldn't come to the last lecture.
Sorry about the delay.
It's fine.
I just recently had fiber optics installed in my house, and it's literally 100 times faster than the old internet connection. It's really phenomenal. So uploading these videos is much easier now. Okay, I'm going to go ahead and get started because there's a little bit of review here. What I mainly want to review is just some free particle stuff before we get going on the real business for tonight. So free particle solutions, if you separate the Schrodinger equation in rectangular coordinates, you get the e to the ikx, the usual plane wave. That's in rectangular coordinates. If you do it in spherical coordinates, the fundamental solutions are radial Bessel functions, spherical Bessel functions, times YLMs. So this is a psi in spherical coordinates. These two sets of solutions separately constitute a complete set. So in the rectangular case, you want to integrate over K. Of course, that's just a Fourier integral. In the spherical case, you'd integrate over the magnitude of K, which is this K thing here without the arrow over it. And you'd also sum over the discrete indices L and M to get, you know, to run over the complete set. So as a result, either one of these two solutions can be expressed as a linear combination of the other set. And the particular expansion that we're interested in is expanding a plane wave as linear combinations of the spherical solutions. Now the K that appears here and the K vector that appears there are related to the energy by the free particle solution or free particle relation, which is E is equal to h bar squared K squared over 2m. So usually it's understood that E and K are related by that formula. So if I want to take a plane wave of energy, this energy here with this wave vector K and expand it as a linear combination of these spherical waves, then I only have to sum it up for one fixed value of K. So it turns into just a discrete sum over L and M, which are the remaining indices. And if you work through the details of it, you get this expansion formula, which I'm not going to take class time to derive, but this is an explicit expression for expansion of a plane wave is a linear combination of the J's, which are the radial wave functions, times the YLMs. Now, by the way, the R hat here refers to the direction of the vector X, which appears on the left-hand side, which is to say that if you convert X into spherical coordinates, R, theta, and phi, then this R hat is just the unit vector that's in the theta phi direction. So YLM of R hat really means the same thing as YLM of theta and phi. I hope that's not confusing. Likewise, the K hat that appears here refers to the direction of the K vector. This is the incident wave in a scattering problem. So K hat here is the unit vector in the direction of propagation of the incident wave. Now, if we take the case in, so if we use the, this formula is just begging for an application of the addition theorem of spherical harmonics, because you're summing on M here times these products of the spherical harmonics. And if you use the addition theorem, then this formula turns into the following. The J is still there, of course, but the product of the Y's gets replaced by a Legendre polynomial of the angle between the two vectors R hat and K hat. Well, that's of course the same as the angle between vectors, the three-dimensional, the non-normalized vectors, K vector and X vector, like so. Anyway, they just call it gamma. And as a result, you get this single sum down the index L involving Legendre polynomials. Now, if in addition you make the incident wave pointing in the Z direction, which people like to do, so that its K vector is the magnitude of K times the Z hat, then this then the plane wave becomes e to the I K times Z, and then the angle gamma becomes the ordinary spherical angle theta, because K is in the Z direction and R is the direction of the R theta phi. So the gamma just becomes theta. And what we have then is expansion in Legendre polynomials about the Z-axis, which is a common form that one sees. It's really essentially equivalent to this expansion up above, but this is another form that you'll see for it. By the way, e to the IKZ can also be written as e to the IK R cosine theta, because of course Z is just equal to R cosine theta, and that's another way of writing this. This is the expansion of e to the IK R cosine theta in Legendre polynomials, given where the coefficients are explicitly given. Okay. Now then, above this line, I've only been using the free particle solutions where the JL type Bessel functions occur, but the solutions of the radial Schrodinger equation have a second set of linearly independent solutions, which are the Y type solutions. Those are excluded if the wave function has to be extended down to the origin because they diverge there, but we'll see in a minute that you need them for scattering theory. Especially in the asymptotic regions, in the asymptotic region or at large radii, you need the Y-type solutions. We will be interested in asymptotic forms of the J's and the Y's, and these are actually more conveniently expressed in terms of the spherical Hankel functions defined down here. There's two types, H1 and H2 of L, and they're just basically J plus and minus I rho. That's all they are. Now the J's and the Y's are real functions. So this J plus and minus I rho are complex conjugate pairs. And they're obviously sort of like, e to the IKX is, is a linear combination of cosine and I sine. Is a similar notion to the way these formulas are constructed. But the advantage of switching to the spherical Hankel functions is that they have particularly simple asymptotic forms that are valid when rho here is the variable upon which the Bessel functions depend. It's usually identified with KR in the actual solution for a free particle, but just calling it rho down here. These formulas are valid. These are the asymptotic forms, and rho goes to infinity. There's a phase factor here, which you see here, and then it's multiplied by e to the I rho over rho for the H1 and e to the minus I rho over rho for H2. And you can see they're complex conjugates of each other. And the H1 is basically an outgoing spherical wave, which you get if you attach the time dependence to it. And the H2 is an incoming spherical wave. So this is convenient for studying the waves in the asymptotic region just to form these linear combinations. Now that's all I want to say for now about free particle solutions. I'll have to come back to them. But the main task for tonight is to solve is to analyze the scattering problem for a central force potential, of which I made a beginning on it last time. So we've got a potential V of R, and we want to solve the usual Schrodinger equation, which I'll just write out. I'll write it out in spherical coordinates. it's the usual thing here, psi of x is equal to the energy psi of x, like so. And we will be interested in energies which are positive or non-negative like this. And we'll usually associate the energy with an associated wave number k by writing E is equal to h bar squared k squared over 2m. It's frequently more convenient to parameterize things in terms of the wave number k than it is in terms of the energy. But in any case, we're interested in unbound, unnormalizable, positive energy solutions of the Schrodinger equation. And that moreover, they have to satisfy the right boundary conditions. So speaking of the boundary conditions, as I explained last time, you take the exact solution, psi of x, let's put this on the left here, and we write this as the incident plane wave, which is e to the I k dot x. So that k is the wave vector of the incident wave. This is the incident part. And then we have the scattered wave, which I'll just write as psi scattered of x. Now this equation actually doesn't have very much content because all it does is define psi scattered as the difference between the exact solution and the incident wave. But it does require more content as soon as we make an assumption about the boundary conditions, which psi scattered has to satisfy. That's to say, we require that it go to as e to the ikr over r times f of theta and phi, like so. And I explained in some detail in last lecture why we do this. This is an outgoing spherical wave. So that's the boundary conditions on psi scatter, that it should be outgoing. The f gives us the angular dependence of the outgoing wave. The 1 over r shows that it falls off, as you'd expect for a wave, leaving, and it has a localized source at a large distance. The wave has to fall off this way by conservation of probability. In any case, this is the asymptotic form. The little tilde here means asymptotic form. What it means is this is not the exact psi scattering wave, but rather the psi scattering wave is equal to this plus correction terms, which die off as r goes to infinity more rapidly than this term, which as you see is the 1 over r. So that's the meaning of the little tilde. It means leading asymptotic form.
I have a question, actually.
Yes, question.
Does it have to go as e to the ikr over r, or can there be like a degenerate, is it allowed to be like a degenerate case where like the 1 over r term is 0 and then there's just like faster? Like, is it not allowed to decay faster?
Oh yeah, there could be other terms out here that decay faster. That's what this tilde means. This tilde
Yeah, but what I mean is it not allowed for like the leading term to decay faster than that?
Oh, well, there's an argument that I gave in the last lecture, which has to do with the conservation of probability. If you imagine that at sufficiently large distance that the potential can be neglected, then this has to be a free particle solution. And what that means is you imagine a spherical wave propagating outwards. It means that in a thin spherical shell, the integral of the probability over that shell, for a given thickness, has to be independent of the radius. Now that requires that the wave function fall off as 1 over r. So in a sense, it's related to the conservation of probability. That's where this comes from.
Makes sense.
Okay. All right. Now, there's other ways of justifying it, but that's one that was the argument I gave last time. It's somewhat an intuitive argument. And by the way, it isn't always true. In the case of Coulomb scattering, the phase shift is more complicated. There's extra terms in this. I might say something about that later. All right. In any case, this is the asymptotic form for the scattered wave, and that's all we know about it. It's all we demand of it, as a matter of fact, is what it looks like at large distances. All right, now then. All right, so our strategy here is going to be to analyze these three terms, the exact term, the incident term, and the scattered wave. And the first thing I'm going to do is decompose the angular dependence of all three of these waves into YLMs. So let's start with the exact solution, the exact solution to the Schrodinger equation. This is a Schrodinger equation represented here in rectangular coordinates, but if we solve it in spherical coordinates, you know what you're going to get is a radial wave function r of r times a YLM. That's what it'll be, theta and phi. And we know that the radial wave function is going to satisfy the radial wave equation, which is h bar squared over 2m, 1 over r squared ddr of r squared dr dr. I'm going to write it out in all detail now. Plus the centrifugal potential is LL plus 1 h bar squared over 2 mr squared. And then we have the true potential V of R. And adding those gives you the effective potential, which multiplies R of R. And then that is equal to the energy times R of R. So this is the radial Schrodinger equation that we solved to get the radial wave functions. All right. The radial Schrodinger equation obviously depends on the angular momentum quantum number L, and it also depends on the energy. And as I said, we're going to express the energy in terms of an equivalent wave number K by writing it as h bar squared K squared over 2m. And so the radial wave function capital R then is parameterized by both the L and the K. I'll write it as R sub KL like this, put the subscripts on it. The K is just another way of talking about the energy of the radial wave function. By the way, the energies we're interested in are greater than or equal to 0. They're positive energies. That means that the wave functions are unbounded. They're not normalizable, and there's no quantization. So the energy has a continuous spectrum running from equals 0 out to infinity. The same thing is true for K. Then K is any number K greater than or equal to 0 going out to infinity. All right. So that's the layout of the solutions to the Schrodinger equation in spherical coordinates. Now the exact solution, which I'll just write as psi of x then, or if you want to, I'll write it as psi of r theta and phi if we want to put it in spherical coordinates. It must be expressible as a linear combination of these solutions. As far as the K value is concerned, there can only be one K value because the solution psi that we're interested in has an energy E. And the K value has to be the same K value connected with the energy E by the free particle relation here. This is just an a way of writing an equivalent K value for corresponding to an energy E. So therefore, this exact solution must be representable as a sum, discrete sum over L and M of some coefficients, which I'll call ALM, times the radial wave function R sub KL of R, times YLM of theta and phi, which I'll just write as YLM of R hat like this. And so this is, I'll box this because this is one of the three things that we need to work on. This is the expansion of the exact solution that gives us the angular dependence expanded as YLMs. This is the way I've done it. We obviously don't know yet what the coefficients ALM are. In fact, we would like to find out what they are as a part of solving this problem, but there certainly exists such coefficients that do this. All right, now, so this is the exact solution. Now, what about the incoming wave? Well, the incoming wave is e to the I k dot x, and I gave you a minute ago in my summary page how this is represented as a linear combination of spherical waves, or this is say free particle solutions in spherical coordinates, and it is this sum. It's the sum on L and M. I'm just copying the formula that was on that page. It turns out the coefficients are 4 pi times I to the L Bessel function JL of K times R times a YLM of R hat times a YLM complex conjugate of K hat. And so this is the expansion of the incident wave, which is the second term here. Here, let me box this up here because this is our basic decomposition of the scattering solution into the incident and scattered wave. So I've taken care of this one and this one, the first two terms. Let's now turn to the scattered wave. As far as the scattered wave is concerned, let's do this. Scattered wave, let's write it as a function of r theta and phi. Of course, we don't know what the scattered wave is, but let's just simply expand this scattered wave as a linear combination of YLMs. So let's put it this way. If we fix the value of R so that we're examining the scattered wave on a sphere of radius R, then let's expand the theta and phi dependence on that sphere in terms of YLMs. If we do that, the expansion coefficients will depend on the value of R. So that means we can write this as a sum on L and M. I'll call the expansion coefficients S sub LM of YLM of R hat like this. Write it like so. So the SLMs are really just defined as these expansion coefficients, or if you like, I'll define the SLMs. They depend on R, by the way. The SLMs of R are equal to just the integral over a solid angle of the YLM of omega complex conjugated times the scattered wave as a function of r theta and phi. This is just undoing the expansion in terms of YLMs. All right. So to pause for a minute and just to review what we've done, we've taken the three terms of the decomposition in the decomposition of the scattering solution, and we've represented each one of them as linear combinations of YLMs here of the angles r theta and phi here, and here. I could have called this r hat also if I'd wanted to. I'll underline the three terms. There's one there, there's one there, and here's one there. I'm sorry, I want to do it here. Here's the YLM there. We've expanded all three of these terms of the decomposition of the wave in terms of the YLMs. All right, so the first box is equal to the second box plus the third box. And the YLMs are linearly independent. So that means we can just strike the YLMs if we also strike the summation over YLM, and we get a valid equation. So let me move on to the next page and write that down, because that'll be the result of the first stage of this operation. There's a fair amount of algebra in deriving this expansion of the scattering problem in spherical coordinates for central force potentials. It's one of the main projects for tonight. Anyway, so just copying this down, then the first step is going to be this, is that ALM times RKL of R. This should be RKL, let me make that clear, RKL of R. That's the first term, is equal to, on the right-hand side, 4 pi I to the L times JL of KR times YLM star of K hat. And then the third term just gives me plus SLM of R. All right, now this is an exact result, no approximation in it, but we don't know what the ALMs are, and we don't know what the SLMs of R are either. So we'll have to do some work to find those. All right, now then, the next step is to take the asymptotic limit of these three terms. To study this in the limit where R goes to infinity. Let's take a look at that. In the first place, we've got the radial wave functions. Let's look at the exact solution on the left-hand side first. We'll take these terms one at a time. For the first term, which is came from the exact solution, we have the radial wave functions, which were the solutions of the radial wave equation. They had to be regular at the origin. That makes them unique apart from a normalization in phase. Now, the question is, what do they look like when R goes to infinity? The key to answering this question is that we're going to assume that the potential dies off rapidly enough that outside of a certain radius, it can be neglected. Or let's put it this way, is that it no longer has any influence on the leading asymptotic form of the radial wave function RKL of R. So this is an assumption. I'll write it out in words here. Assume that V of R goes to 0 fast enough so that as R goes to infinity, we have the radial wave function RKL of R should be dominated by, should the leading order term should be the same as that of the free particle solutions, JL of KR, YL of KR. And what I should say is a linear combination of these two. All right. Now, the JL and YL at large radii fall off like 1 over R. So in effect, what this statement is saying is that we're going to assume that V dies off rapidly enough so that whatever corrections it makes at some large radius R, they don't affect the leading term here. The leading term is the same as that of the free particle solutions. I mean, from a kind of a more naive or simple-minded point of view, we're just saying that if you go far enough out, you can neglect the potential. That's the idea. All right, but in any case, this is an assumption which one can examine. And this is examined in the notes. I'm not sure how much time I'll spend in lecture on it, but it's actually examined quite carefully in the notes. Now, the J's and the Y's are not the most convenient form for looking at asymptotic forms. Rather, the spherical Hankel functions are. So let's express it this way. Let's write RKL of R. We're going to assume asymptotes to a linear combination of the spherical Hankel function. So let's call the coefficient B here like this, and let's call it H1L of KR for the first one. And let's call it B star for H2L of KR. We'll assume that it asymptotes like that. Now, I'm making these two coefficients of these two spherical Hankel functions complex conjugates of each other for the following reason. The radial wave function is a real differential equation. And so it possesses solutions, radial wave functions, which are real. So let's assume we've done that. That determines the radial wave function. It determines its phase to within a plus or a minus sign. Doesn't determine the normalization yet, but at least we know it's a real wave function. So if we do that, then the right-hand side has to be real. But the two spherical Hankel functions, H1 and H2, are complex conjugates of each other. So the coefficients have to be two. These two terms have to be complex conjugate. So that's where this expression in this form came from, like that. All right. Now let's write this B. This B, by the way, depends on the value of L. So let me put a B sub L on it. It actually depends on K as well, but I'll just write B sub L. So let's write B sub L in terms of its magnitude, B sub L, and its times its phase, e to the I, which I'll call delta L, e to the I delta L. And so if we do this, then we get the exact solution, asymptotes to what? To the magnitude of B sub L times e to the I delta L times H1 L of KR plus the complex conjugate. All right. Now then, next let's do this. This B sub L is a real number. Let's absorb that into the normalization of the radial wave function. And if we do that, that means the radial wave function is now determined in both normalization and phase to within a plus or a minus sign, because that's the only thing that's left over when we demanded that it be real. And so then I can rewrite this equation if I want to without the B sub L, but I won't bother to do that. What I will do is take the asymptotic forms of the HL and its complex conjugate and write them in. And if we do this, then what we get is RKL of R as the asymptotic form of e to the I delta L times the asymptotic form of H1KL. Well, that's the same thing as I to the minus L plus 1 times e to the I KR, and now I'll include the delta L plus delta L over KR. That takes care of the first term. And then the second term is a complex conjugate. It's I to the L plus 1, e to the minus I, KR plus delta L divided by KR. And let me box that, because this is the asymptotic form of the radial solutions to the radial wave equation for the exact solution. I mean, solving the radial wave equation for the radial wave functions requires the knowledge of the potential. And there's a lot of different potentials. But what we see here is that if the potential dies off rapidly enough, then the behavior of that solution at large radii is determined by one parameter only, which is this delta L. Delta L was the phase part of this coefficient BL. This is usually called the phase shifts. The delta L's are called the phase shifts. There's one for each L. They actually depend on K as well. You can write them as delta L of energy E if you want to emphasize that. But in any case, they're called the phase shifts, and they turn out to be an important set of parameters for the scattering problem in the case of spherically symmetric potentials. All right, there's like one parameter for each L value, which is determined by the potential. All right, now then, that takes care of the asymptotic form of the exact solution. What about the asymptotic form of the incident wave? Well, the only issue there is the Bessel function JL. And JL, if you write it in terms of a spherical Hankel functions, is H1L plus H2L. over 2. I mean, that's just what it is, because H1 and H2 are J1 plus and minus IY. So if you add them up, the IYs cancel and you just divide by 2. So what that means is that in the case of the free particle, is it still here on the page here? Let me clean things up here a little bit. Center this. So taking the asymptotic form of the JL and keeping the rest of these coefficients here, then what I get is, let me just call it the free particle solution. The free part, not the free part, I mean the incident part. The incident part goes like, what does it go like? It goes like 4 pi I to the L. Then the asymptotic form of JL, which has got a 1/2 from that 1/2 there. And then the asymptotic forms of the H's, the 2 H's. So this is I to the minus L plus 1 times E to the IKR over R plus I to the L plus 1, this is over KR, times E to the minus IKR over R, KR. All right, that takes care of the incident wave. And now what about the scattered wave? Can we say anything about the asymptotic part of this SLM? The answer is yes, but let me do it on another page here. Let me remind you, the SLM was defined by writing the psi scattering wave. The psi scattering wave of R theta and phi was equal to a sum on L and M of SLM of radius R times YLM of R hat. But we know that this asymptotically has to go as E to the IKR over R times the scattering amplitude, F of theta and phi. Let's take the scattering amplitude and expand it in terms of YLMs. Let's call the coefficients F sub LM times YLM of R hat. Let's write it like that. And if we do, then you can see that the SLM is the coefficient of the YLM. So you get SLM then of R asymptotes 2 E to the IKR over R times the FLM coefficient. It's related to the YLM expansion of the scattering amplitude. The scattering amplitude is our goal here. We'd love to find that because you square it, you get the cross section. So keep that in mind. It's sort of an obvious strategy, since it depends on direction. It's an obvious strategy to expand it in terms of YLMs, and that's what these Fs are, is the coefficients of that expansion. But in any case, to go back to the previous page, then, as far as the scattered part, the scattered contribution, the last term here, it asymptotes to, as I just explained, E to the IKR over R times FLM. And let me box that as well. All right. So these are the leading asymptotic terms of the 3 parts of the wave: the exact solution, the incident wave, and the scattered wave. All of them go as 1 over R. So they all have the same dependence as R goes to infinity. These are therefore the same, they have the same behavior as R goes to infinity. And so any correction terms are in all 3 cases are something that goes to 0 faster than 1 over R. So what that means is that if I write the first one is equal to the sum of the next 2, the result is actually exact, even though we obtained it by taking leading asymptotic forms. That's because the leading asymptotic form is uniquely determined by the function. I mean, there may be higher order corrections, and you can worry about them as well if you want, but the leading term is uniquely determined by the value of the function. So all 3 of these have leading terms that go in the same behavior, and so they have to add up to each other. And so let's put those together then into a single equation, which we can now analyze. So this is the next phase of this calculation. The first one was to expand all 3 terms in YLMs. The second step was to look at the asymptotic limit of the result, and that's what we got now. So let's write this out. So the first term is we multiply by the ALM times the YR RKL. Here we've got this. So to write this out explicitly, we have ALM we have this thing here, which is I to the minus L plus 1 times e to the I kr plus delta sub L divided by kr. Then we have the complex conjugated of that I to the L plus 1 e to the minus I kr plus delta L divided by kr, like so. That takes care of the left-hand side here. Now we'll do the free particle part. And here I did it down here already. I've got this all written out, except I forgot to multiply this by YLM of K hat. So I need to include that. You can see that it's here. Here's the YLM of K hat. There's the J. The J asymptotic form is what we have here between the curly brackets, and there's the YLM of K hat there. So that's what this is. So let's put this into our equation. This then becomes equal to 4 pi I to the L times 1/2 times I to the minus L plus 1 e to the I kr over r plus its complex conjugate I to the L plus 1 e to the minus I kr over r. Close that and then multiply by YLM of K hat. And then all we need to do now is to add the part that comes from the scattering term. And so then this is plus e to the I kr over r times FLM. All right. And as I just explained, this equation is actually exact. All right. Now, this equation has linear combinations of, as you can see, outgoing waves here, here, and here in the exact solution, the incident wave, and the scattered wave. And it has incoming spherical waves in the exact solution and the incident wave, but not in the scattered wave, because the scattered wave doesn't have any incoming part. That's what the scattered wave is all about. It's outgoing. These are really the physical boundary conditions that are imposed here, meaning there's no incoming part of the third term. However, these outgoing and incoming spherical waves are linearly independent functions. So the coefficients separately vanish. So let's use that fact to analyze this. In particular, let's start with the incoming waves. That means these two terms have to cancel one another. And if I write them out explicitly, well, you can see there's some common factors involved. Let me use red ink to mark off the common factors. Between these incoming waves, the I to the L plus 1 is a common factor. We can take that out. The kr in the denominator, there should have been krs here. Kr in the denominator there is a common factor. And e to the minus I kr is a common factor there, but there's this extra phase shift in the first term. And so let's copy this now and clean it up a little bit. We get ALM, and then copying what's left over, we get e to the minus I delta L from here, from that phase shift, is equal to, on the right-hand side, 4 pi times I to the L times 1/2 from there. And then what's left over is the YLM of K hat complex conjugated. Okay, so we get that. You know, the K hat is the direction of the incident wave. That's just a parameter of the problem. And the delta L was the phase shift from the exact solution, the asymptotic form of the exact solution. We don't know what that is, but it was just one parameter for each value of L. And what this shows you is that the expansion coefficients, these A's, are the expansion coefficients of the exact solution in terms of the radial eigenfunctions. And you can see then that I know what the phase shifts are, I can solve for those ALMs. So this is actually quite interesting, because it means it's possible, knowing the phase shifts, it becomes possible to solve for the expansion coefficients, even without knowing what the exact radial wave functions are. We're just working with the asymptotic forms. All right, in any case, this is an important intermediate result. Now, this should have been starred here. Now, if I put this in here, then this 4 pi I to the L times the 1/2, and the YLM of K star here, these two factors taken together are the same thing as the ALM times e to the minus I delta L. okay? Because e to the minus I delta L is what you see here. I'm just using this formula up here and connect these two things together. So now let's take a look at the outgoing waves, of which there's three terms here, like this. There's a common factor of e to the I kr over kr. Let me put a k down here and a k up there to make all three factors the same. So when I set that equal to that plus that, I'm going to get a common factor of e to the I kr over r, which will cancel out. So I'll circle in red here what we can just eliminate from the algebra here. The I to the minus L plus 1 is the same on both sides. The ALM is the same on both sides. And if I do the algebra of this, then I can write this way, is that ALM, the only thing that's ALM, let me write it this way. Let me get it right. ALM, there's a factor of I to the minus L plus 1, which is common to these two terms. Then the term on the left-hand side had an e to the I delta L. And the term on the right-hand side had an e to the minus I delta L, comes over the minus sign. And so that is equal to, that's equal to what we've got in the third term, which is K times FLM. FLM, remember, is what we want to find. All right, now then, on the other hand, the ALM, I can solve for the ALM in terms of this stuff and plug it in there, in which case this now becomes equal to 4 pi I to the L times 1/2 times YLM of star of K hat. I'm taking this, I'm solving for ALM, and I'm solving for ALM and plugging it in there. There's an e to the I delta L that comes from bringing that over. Then I have the rest of this. I have I to the minus L plus 1. So I'm just doing the algebra here. Then this quantity here is the same thing as 2I times sine of delta L.
That should be an e to the minus I delta L in the exponent, right? On the line above.
This is e to the minus I
No,
delta
below
L.
that.
When I bring it across, it becomes a plus, and that's why I put it as a plus here.
No, in the line in between.
Here, you mean?
Yeah, that
It should have been a minus. Yes, you're right. Yes, minus. There's 2I sine. That's where this came from. Okay, so we can now clean this up. I to the L times I to the minus L plus 1 times I, they just all cancels and gives you 1. 1/2 times 2 gives you 1. And so we end up with the following, and then let me divide by the K here to solve for FLM. So what we get is FLM then is equal to 4 pi over K. That's from this 4 pi here. Let me save the YLM star in a minute. Let's copy this, e to the I delta L times the sine of delta L times YLM star of K hat. And let me box that because this is the main conclusion of the analysis of the incoming and outgoing waves of the asymptotic forms of the three terms of the decomposition of the exact scattering solution. And we see we have an expression for the YLM amplitudes or coefficients of the scattering amplitude written in terms of stuff that we know. We know everything on the right-hand side except for these delta L's. Again, knowledge of the delta L's is giving us information about the expansion coefficients that we need. I can then use this by multiplying by YLMs and summing to get f of theta and phi then is equal to let me write it this way, is equal to 4 pi over K. In fact, excuse me, let me put it on a summary page because it's going to be a formula we'll want to use in a minute and come back to. Let me put it in a summary page here. So it's going to be our solution for the scattering amplitude. And it is this, is that f of theta and phi then is equal to this thing summed over L and M multiplied times YLM. So it's going to be 4 pi over K. I'll take that out. The sum on L and M. And then we have e to the I delta L times sine delta L times YLM of R hat times YLM complex conjugate of K hat. And let me box that because that's in effect the solution for the scattering amplitude expressed in terms of these parameters, these delta L's, which are these phase shifts. All right. Let's see. Allow me to make a few other comments about this expansion before I leave it. I can do. I don't think I'm going to need it. I tell you what I'll do. Let me get a different pad of paper here. We'll do this way. Let me make some comments about this expansion. So this is a principal result. This is our scattering amplitude, you see. Let me make a few extra comments about this. In the first place, if we can apply that, we can use the addition theorem for the spherical harmonics. And again, allow me to write the angle between R hat and K hat as an angle, which I'll call gamma. And if I do that, then I get F of theta and phi is equal to 1 over K times the sum now only on L, because the addition theorem involves a sum on M of these products of YLMs. Now you get just a sum on L. You get a 2L plus 1. You get the e to the I delta L times the sine of delta L. That I'm just copying from up here. And then the product of YLMs gets replaced by the Legendre polynomial of cosine gamma. All right, so gamma is this angle. Another special case is to let K be equal to magnitude of K times Z hat, which says that K dotted into X is the same thing as KR cosine theta. Now, in that case, this implies that gamma is just equal to the angle theta, because the K direction becomes the Z hat direction, and the angle with R hat is just this usual spherical angle theta. So in this case, what we find then is that F of theta is equal to 1 over K times the sum on L. It's almost the same formula, 2L plus 1 times e to the I delta L times sine delta L times PL of cosine theta. And let me box that too, because it's essentially the same formula, but it's in somewhat more familiar form, and it's also one that's tied to the coordinate system now. And it makes sense too in a certain way, because if I have my potential, which is spherically symmetric somehow here, some potential V of R like this, and let's say this is the Z axis, and I send in waves here which are propagating in the Z direction, then it's certainly physically plausible on the basis of symmetry that the scattering amplitude should be independent of the azimuthal angle about the Z axis. It should depend only on theta. And if it should depend only on the scattering angle, which is theta, you see. And in fact, it does. And if it depends only on theta, then it can be expanded in Legendre polynomials. And this series then gives us the explicit expansion with all of the coefficients written out explicitly, expressed in terms, once again, of these phase shifts delta L. So these are just variations then on this earlier result, which I obtained up here like this. All right. Now I want this to be a summary page, so I don't want to mess up with it too much. But let me tear this off and let me make some developments from this formula. One of the things we know is the differential cross section is the square of the scattering amplitude. Very simple result, very nice result. And if I square this series, what we get is we get 4 pi over K quantity squared. Then we get a double sum on L and M and L prime and M prime. And then we get phase factor e to the I delta L minus delta L prime, because one of the factors has to be complex conjugated when we square it. Then we get sine delta L times sine delta L prime. Then we get YLM of R hat times YLM L prime M prime of R hat times YLM star of K hat. Let's see, this one should have been starred, the YLM prime, times YL prime M prime of K hat now without a star. So I just multiplied this out times its complex conjugate, and there's no simplification. You just have to write out all the terms, of which there are, 8 or 10 of them like that. Okay, you get this double sum. Now, as I say, there's no simplification. And the reason is this, is that, well, I mean, the effect of it is this. Let me say, first of all, that the expansion above, which is one of our main results tonight, of the scattering amplitude given here in terms of these YLMs, expressed with coefficients expressed in terms of the phase shifts. This expansion is sometimes called the partial wave expansion of the scattering amplitude. And each of these L terms is called a partial wave contribution, or LM term is a partial wave contribution. So when we square the scattering amplitude to get the differential cross section, the various partial waves interfere with one another and they don't really simplify. But what that means is that if you plot the differential cross section, let's say as a function of theta, if it were, pointing in the z direction, it would just be a function of theta. Typically what you find experimentally and theoretically both is you find oscillations in the cross section as a function of angle in the cross section. It oscillates. It's not a smooth function. It's smooth function, but it's an oscillatory function. And those oscillations come from the interference of the various partial waves. All right. Now, on the other hand, if we want to compute the total cross-section sigma, which is the integral of the differential cross-section over all solid angles, then you can see on carrying out this integral that the YLM of R prime and the YLM complex conjugate L prime M prime are going to combine together by the orthonormality of the YLMs and just give us a Kronecker delta LL prime and MM prime like that. And as a result, the double sum will turn into a single sum. So this becomes 4 pi over k squared like this times the sum on just a single L and M. The phase factors cancel because L prime equals L. The two signs combine together to give you sine squared delta L. And then what's left over is just the YLMs of the Ks. We got YLM star of K hat times the same LM YLM of the same K. And so now we get to use the addition theorem for spherical harmonics once again. If you have the sum of n of two y's of the same k's, like the same angles like this is the same thing as 2l plus 1 over 4 pi times a PL of the angle, a cosine of the angle between the two. But if the two are equal, it's a cosine of 0. Cosine of 0 is 1. PL of 1 is equal to 1. So it just becomes 2l plus 1 over 4 pi. And so one of these 4 pi's will cancel one of those 4 pi's. And we get a useful formula for the total cross section, which I'll now write here. We get sigma is equal to 4 pi over k squared times now just a sum on L of 2L plus 1 times sine squared of delta L. A much simpler expression for the total cross section. So the theory gives us a fairly simple expression for the scattering amplitude and a quite simple expression for the total cross section. Okay. Now, that's one of the big jobs I needed to do tonight was to derive this. It takes a long time to do it. I'm sorry with all the details, but these are the main results of this analysis of scattering for a central force potential, these expressions. Before I go on, are there any comments or questions about what I've done so far?
Yeah. How do you find what the delta L's are?
Yeah, that's my next topic.
Okay.
Any other questions?
Is there something interesting that can be said about this quantity 4 pi over k that keeps showing up? Or is it just a
Well,
constant
not
factor?
that I know of. It's just the factor that occurs. I mean, dimensionally, it has to be that way because the F has dimensions of length. Its square is a cross section has dimensions of area. So
Okay.
dimensionally, it makes sense, but and the rest of it's dimensionless. But That's the best I can say.
Okay,
Um,
thank you.
So as was pointed out, these expressions point to the fact that there's a lot of interest in the phase shifts, because if you know them, you can calculate everything you want to know about the scattering problem. The differential cross section and the total cross section is the usual goals. So what about these phase shifts? What are they? So in the first place, let me give you an intuitive understanding of what they are. The phase shifts, I'll remind you, were determined by the asymptotic form of the exact radial Schrodinger, of the solution of the exact radial Schrodinger, exact radial wave functions. As I say, the asymptotic form was this. It was these phases I to the minus L plus 1, and then we have E to the I kr plus delta L over kr. And then we have the complex conjugate I to the L plus 1, the incoming wave E to the minus I kr plus delta L over kr. On the other hand, for a free particle, we just need the asymptotic forms of the J-type Bessel functions, and they look pretty similar, but there's no delta L in there. In fact, it's the same except there's no delta L. So I just write it out. And so one of the things that comparing these two equations tells you is that in the case of a free particle, the phase shifts delta L are equal to 0. Now there's another way of viewing this. So this you might say is just a normalization or a convention for the phase shifts, but it's convenient. The phase shifts vanish for the case of zero potential. So the phase shifts are in effect making some kind of a measurement of the effect of the potential. And here's a way of visualizing it. Is this e to the minus ikr over r is an inward traveling spherical wave. Imagine you've got your potential down near the origin, but you're on a large sphere far away from it, and you can put transmitters all over the surface of the sphere and coordinate them somehow with a button you can press. And so what you do is you launch waves spherically inward, spherical waves inward from the surface of your sphere inward towards the potential. And those waves travel inward, they interact with the potential, they sort of focus around the origin as well as interacting with the potential, they reflect and come back out. And when they do, you can see the reflected wave, and you can make a comparison of the phase of the reflected wave compared to the ingoing wave. Now, if you do that, and then you get a certain phase shift. And if you compare that phase shift to the phase shift you'd get for a free particle, you can do that for a free particle or for a potential. You can do it for any potential you want. Do it for a free particle first, and then do it for the potential, and compare the two. Well, the comparison is what gives you the delta L. The delta L is the phase shift relative to the free particle phase shift. And that's at least it gives you a picture of how to think about these phase shifts. It's not exactly a practical way of calculating them, but at least it gives you an idea of how to think about them. All right. Now, how to calculate them? Well, one of the ways of calculating them would be numerically. You would take the radial Schrodinger equation for a given value of L. You'd set up the regular boundary conditions at r equals 0, and you just integrate the wave function out until you are well out beyond the range of the potential. And out there, you ought to be getting free particle solutions, which would be linear combinations of j's and y's. And so comparing your numerical solution to j's and y's, you can read off the coefficients, and from that, you can find the phase shift. So numerically, one can do that. Principle, it can do that. In practice, it's done that way too. Notice it's only 1D wave equations too. It's not that bad to do. You have to do it for every L, however. All right. Let me tell you something else about phase shifts. They're conveniently analyzed in terms of by means of WKB theory. Let me explain this. Let's do a one-dimensional WKB problem on the radial Schrodinger equation. So let's draw a radial axis going out like this, and allow me to plot an effective potential. In fact, let's start with the free particle for which the effective potential is just the centrifugal potential. So for a given value of L, it looks like this. It's L times L plus 1 h bar squared over 2 mr squared. That's the centrifugal potential. To do WKB theory, we're going to pick an energy E like this. And we're going to imagine launching a wave which comes in from the left like this. It'll climb up this potential well, which is just the centrifugal potential. It'll reach the turning point. Let's call this R0. And it will reflect and it'll go back out. So you got a wave coming in like this, and you got a reflected wave coming back out. That's the idea. Okay. Now, the question is, what's the location of the turning point? It's easy enough to set that up. All we need to do is to equate the energy to the value of the centrifugal potential. So E is equal to h bar squared L plus 1 divided by 2m, and I'll call this R naught, so it's R naught squared like this. And as far as the energy goes, let's once again write it as h bar squared k squared over 2m to express it in terms of an equivalent wave number k. If we do this and we can solve for the wave number k, the h bars cancel, the 2m's cancel. And if you solve this, and let's take L times L plus 1, and let's just replace it by L squared, which is okay if L is big enough. So if we do this, then we get a simple formula. What you find is you get the R naught. The R naught is equal to L divided by K. So that gives us the value of the turning point. Let me write this in a slightly different form. Let me write it as L is equal to R naught times K. So these are the relations for the turning point for the free particle. Now let's add a real potential to it, but let's suppose the real potential is localized. Let's suppose it looks like this. It's something like this. So let's suppose our real potential is, so this is the V of R here. And let's suppose it's got some range, which I'll call lowercase a. Now you can see the way I've sketched it, the range of the true potential lies inside the turning point for the given value of energy that I had. If I chose a larger L value, by the way, I'd get another turning point, which would be further out, R0 prime. The turning point moves further and further out, the higher the L value is. So where the turning point is depends on the L value. But the way I sketched it, the turning points, the two of them that I sketched, are out beyond what you'd call the range of the potential. Now, think about the WKB solution. What this means is that the total potential, if the centrifugal plus the true potential, is almost the same as the true potential alone coming in as far as the turning point, the way that I've sketched it. So the evolution of this WKB wave is going to be largely unaffected by the true potential. It'll reach the turning point, it'll reflect, and it'll go back out again. Now there will be some exponentially decaying tail of this wave, which will penetrate into the classically forbidden region. And that tail will in fact interact with the true potential down inside here. But it does so only in the exponentially decaying tail of this tunneling solution. This in the situation which I've sketched. Furthermore, if I increase the value of L, then you see there's a greater distance to tunnel through. And so therefore the true potential will have less and less effect. As L increases, there's less and less effect. So what this picture shows you is, just without doing any detailed calculations, but just understanding a little bit about WKB theory, is that it shows you that there is a minimum value of L where the potential starts to get engaged. And for higher values of L, the dynamics is really the same as that of a free particle with only small exponential corrections. And so what that means is that in these L sums, which you see here, the phase shifts are going to go to 0, that is to say the free particle values, when the L value gets large enough that the turning point in the centrifugal potential gets out beyond the range of the true potential. So what that means is that there's a cutoff for an L max, a cutoff in these series here. These series are dominated by a certain number of L terms, and roughly is L max. And this is basically K times the range of the potential, Ka. This is what I get by setting A equal to the R naught for the turning point. And what we also see is that for L much greater than or comparable to L max, we find that the delta L's must go to 0 exponentially. Exponentially because they're riding on the they're riding on the exponential tail of that tunneling solution. Okay. So this is important qualitative information about this partial wave expansion that we see in this problem derived by WKB theory. There's a lot of aspects of this problem that can be analyzed by WKB theory because the radial wave equation is 1D, and so you can use all those techniques. You can look at resonances, you can do all kinds of interesting things with WKB theory in this problem. All right, now then, so in any case, this is an important result. It gives us our L max is just cut off at Ka. Okay, now I think that is that's the main things that I want to say about the phase shifts, their cutoff properties, various ways that one might use to compute them, including numerical ways. Sometimes one can compute them analytically. I'll show you an example of that in a minute. Are there any questions before I go on? If not, then the next stage is to solve a real problem best we can. The real problem is probably the only reasonably tractable problem in central force scattering, and that's the case of the hard sphere. But you can learn a lot about waves and how they operate, and good quantum mechanics by studying this. So as a function of r, let's plot the potential V of r. If it's a hard sphere, it has a certain radius a, and inside that radius, the potential is infinity. Outside of that radius, the solution is that of a free particle, which means it's a linear combination of JLs and YLs for the radial wave function. The radial wave function, the r sub KL of r, has to vanish at the boundary of the hard sphere. It has to look something like this, starting out. All right, so for r greater than a in the exterior region, what is the solution? RKL of r must be a linear combination of the free particle solutions. Allow me to write it this way as B times H1L of KR plus B star times H2L of KR. This is the same expression I wrote down earlier when talking about the asymptotic form of the exact radial wave functions for some potential V of r. However, in that context, that was just an asymptotic form of the radial wave functions. We hoped the potential died off fast enough that it would be essentially free at a large enough radius. This is a little different situation here because potential vanishes identically outside radius a, and so we really do have free particle solutions out there. So this is not an approximation that this is exact in that range for some coefficients b. Again, I made b and b star in here because h1 and h2 are complex conjugates, and we'll assume that we made the radial wave function real, which we can do. Now, as we did before, let's take this b and break it up into its magnitude and phase, which we'll call e to the I delta. The delta is really delta L. The b depends on L2. I want to put that in there. And as we did also before, let's absorb the b sub L magnitude into the normalization of r. And if we do that, then we get RKL of r is equal to e to the I delta L times H1L of KR plus the complex conjugate, which is e to the minus I delta L H2L of KR. And what we require is that this must equal to 0 at r equals a. This is the boundary condition, the inner boundary condition at that point there. So if I set r is equal to a in this expression and set it equal to 0, you see I can solve for the phase shift e to the I delta L. And so here's what we get: is we get e to the, it's actually e to the. So look at the algebra. I'm gonna set r is equal to a here for the boundary of the hard sphere, and then I'm going to set the whole thing equals to 0 at r equals a, like that. I'll bring the minus delta term to the other side, gives a minus sign, then divide by e to the minus, and then solve for e to the I delta L. So this gives e to the 2I delta L is equal to the minus sign H2L of Ka divided by H1L of Ka. And so you see we have an example now where we have an analytic formula for the phase shifts given in terms of spherical Hankel functions. If you were working on a computer and you had nice subroutines for the Hankel functions, it would be easy to compute the phase shifts and start adding up the series for the cross section and so on. In fact, I did that once. It's not that hard to do. Okay. All right. So this is the result, but since it's expressed in terms of special functions, it's a little hard to get some intuition for it. So the next step is to examine this in the two limits that we can look at. One is a limit where Ka is much less than 1, and the other one is where Ka is much greater than 1. These are respectively the low and high energy limits. Let's take a look at the low and high energy limits of this hard sphere scattering. To start out, let's take, for starters, let's take the low energy limit where Ka is much less than 1. By the way, I'll remind you that in the Born approximation, which you can see is in a completely different universe that we derived in the previous lecture, I explained the Born approximation is basically a high energy approximation in the scattering on scattering problem. But what we're getting in this analysis is we're getting access to low energy scattering as well. This is important because there's a lot of important applications of low energy scattering. I mean, Bose-Einstein condensates are full of it. So if you ever get into the theory of that, you'll be doing a lot of low energy scattering. Any low temperature stuff will give you that. In any case, let's look at the limit Ka is much less than 1. Now, K is like 1 over the wavelength lambda. So the picture here is you've got a little hard sphere that isn't very big. And then you've got long wavelength waves coming in where the wavelength lambda is much larger than the size of the sphere. And it's going to be, you know, it's going to be hitting that sphere and scattering off of it like that. So here's a little game you can play at this point. Challenge your physical intuition. Now ask yourself, what do you think is going to be the scattering amplitude or differential cross section here? In particular, how is it going to depend on angle? Will most of the scattering be in the forward direction? Will most of it be in the backward direction? Will it be isotropic? Will it be coming out to the sides? What do you think is the answer? Use your, you don't have to tell me because we can't do it very well anyway over Zoom, but just challenge yourself a little bit to try to use your physical intuition to guess what the answer is going to be in case you don't know already. All right, so let's think about it. So let's analyze it and see what it is. So for this purpose, we need the small argument limit of the Hankel functions, or the spherical Bessel functions. Let's write this in terms of spherical Bessel functions. So e to the I 2I delta L is equal to, and I'm going to write the Hankel functions in terms of J's and Y's. So it becomes a minus, so the H2 is J minus IY. So I'll write as JL minus IYL divided by JL plus IYL. Okay, and this is assumed evaluated at R equals A. So these are evaluated at J. For example, we have JL of KA. That's what is supposed to be in here. Now let me get my my summary sheet for properties of free particle solutions. Here it is. I think I earlier talked about the large argument limiting forms, but here's the small argument limiting forms for the spherical Bessel functions. By the way, if I wanted to, I could teach a course someday on special functions and how you derive these things and use steepest descent arguments and contour integration and all this stuff. There's a whole machinery for doing this, but you can look these things up in books like reference books like Abramowitz and Stegun is a good one to have. Abramowitz and Stegun is very cheap, and I recommend that you buy one. You can get it off Amazon for, I don't know what it is, but it doesn't cost much at all. The Dover edition now, and it certainly is useful to have if you're going to have a career as a physicist. All right. Anyway, these are the limiting forms. The rho here is the variable that the Bessel functions depend on. You can see that when rho is small, that the J-type Bessel function is also small. In fact, it goes like rho to the L power. this is clearly an example of the general rule that we saw last semester, that radial wave functions in the Schrodinger equation go like r to the L near the origin. That's what this is. But we've also got the explicit constant out front, that this double factorial in the denominator. That, of course, depends on the conventions for the normalization of the J's and the Y's. So those things are conventional. But anyway, that's what it is. By the way, the double factorial is just notation, like it just means you count by twos instead of ones. For example, 5 double factorial means 5 times 3 times 1. You just count down by twos. Now, as far as the y is concerned, so the J-type Bessel function is small and positive when rho is small. The Y-type Bessel function, when rho is small, looks like this. It goes like 1 over rho to the L plus 1. This is the other class of solutions we talked about last semester. These diverge at the origin and are therefore not allowed if the solution you're talking about goes all the way down to the origin. And again, here's the normalization and so on. So we use these formulas then. So to go back then, our phase shift for the free particle is the, yep, here it is. The phase shift for the free particle is given in terms of J's and Y's. It looks like that. Allow me to divide through by the Y, which is the larger part, and define epsilon is equal to JL over YL. That makes the epsilon a small number. It's actually going to be a negative number. It makes it a small number because the J is small and the Y is big. So this thing becomes equal to minus epsilon minus I divided by epsilon plus I. And if I multiply the numerator and denominator by I, no, let's see, I want to multiply it by, let's see, let me do it right. I want to multiply the numerator and denominator by, yeah, multiply numerator and denominator by I. Then this turns into 1 plus I epsilon divided by 1 minus I epsilon. And this is equal to 1 plus 2I epsilon if epsilon is small, which it is in our problem. And again, if epsilon is small, it becomes equal to e to the 2I epsilon. Again, assuming epsilon is small. So what we see is the delta L is basically equal to this epsilon, which is J sub L of Ka divided by YL of Ka. So this is a simplified version of the phase shifts in the case that Ka is small. Now, if I then put in the small limiting forms here, I'm going to divide the J by the rho, excuse me, the J by the Y. Then what you get is, you get with an overall minus sign, you get Ka to the 2L plus 1 power divided by 2L plus 1 double factorial times 2L minus 1 double factorial. And thus we end up in this small Ka limit, small energy limit. We end up with an explicit formula for the phase shifts, delta L. Here they are. Ka is assumed to be small here. So what we see is that the phase shifts are small because they involve powers of Ka. The biggest one is delta 0. That's where you get Ka to the first power. By the way, the factorials just make it even smaller. So the conclusion of this formula is that the entire series is dominated by, as the phase shift, the largest phase shift is delta 0, and all the others are much smaller still. So we really only need one term in the partial wave expansion. And the delta 0 for explicitly is just simply minus Ka, because 2L plus 1 equals 1, and the double factorials just give you 1. So this gives us the phase shift then for the L equals 0 partial wave in the case of low energy scattering. Now, if we now go back to our formulas, let's have them here. Here they are for low energy scattering. We've got, oh, let's see here. Did I, let's see, I thought I did this somewhere here. I converted this upper formula into Legendre polynomials. Let's see if I can find it here. may have lost it. I may have lost it here. Let me find it here. Yeah, here it is. This upper formula was expressed in terms of an arbitrary direction of incident wave k hat. But if we made k hat in the z direction, we get this equivalent expression down here. Let's look at this one. And let's just restrict this to the term L equals 0, and let's make delta sub 0 small. So if we do this, then e to the I, so just a single term L equals 0, the 2L plus 1 becomes 1. E to the I delta L becomes 1 because delta L is small. Sine delta L becomes delta L, except it's just delta 0. The P0 of cosine theta, the zeroth order Legendre polynomial, is just equal to 1. And so what we get is we get f of theta is equal to 1 over k, the leading factor, times delta 0. And that's equal to delta 0 is equal to minus ka. And so this just becomes equal to minus a. So the scattering amplitude for low energy scattering from a hard sphere is just f of theta equals minus a. Nice simple result. And in particular, notice that it doesn't depend on the direction. The scattering is isotropic. The scattered wave is the same amplitude, same intensity going out in all directions, including the forward direction and the backward direction and everything. I don't want to spend all night looking for earlier pages, but somewhere here I had a picture of this scattering. And I asked you to think about using your physical intuition for what the scattering is going to look like. And then now we can fill it in. I've got it here. Good grief, I don't know where it is. All right, so what it's going to look like is this. You're going to have these long wavelength waves coming in like this, hitting this small object. And the scattered wave is going to be isotropic. Is that a surprise? Anyway, that's what it is. Scattering of scalar waves off of a small object is isotropic. Okay. This is called S-wave scattering. And S-wave scattering, we've worked it out here for the case of a hard sphere only, but in fact it applies to any localized potential. If the wavelength of the incident wave is much larger than the range of the potential, then the scattering is going to be S-wave scattering. It's worthwhile mentioning that this situation occurs in Bose-Einstein condensates. You may have seen the blurb in one of the recent homework problems where the goal was to derive the Gross-Pitaevsky equation. This was the boson version of the Hartree-Fock equations. I didn't call it the Gross-Pitaevsky equation in the homework assignment because I didn't want you to look it up. I wanted you to derive it for yourselves. But in any case, that's what it is. In Bose-Einstein condensates, they are usually almost always they're dilute gases, which means that the distance between the atoms is small compared to the size of the atom, large compared to the size of the atoms. Moreover, in order to achieve the condensation, you'll be learning about this in Physics 211. In order to achieve the condensation, the de Broglie wavelength corresponding to the temperature has to be comparable to or larger than the interparticle separation. So what that means is that the de Broglie wavelength is therefore much larger than the size of the atoms themselves. It's a picture just like this. So that means the interaction between the atoms in a Bose-Einstein condensate is governed by S-wave scattering. I mean, atoms are complicated things, and you might think it would be really complicated to figure out how one would scatter off of the other. But at low energies like this, being S-wave scattering, the scattering is determined by a single parameter, which is this delta 0. It's the phase shift delta 0, which is effectively the range of the potential of the interaction. And that's the only parameter that's needed. So this is why in these theories, people use delta function potentials, because you adjust the strength of the delta function potential to give you the right phase shift for S wave scattering, and then you've captured all the physics. Okay, so this is halfway through hard sphere scattering, because the other half is to look at the high energy limit, which is also very interesting from a different standpoint. And we're out of time tonight, so I'll do the high energy limit the next time we meet. I want to mention one thing though before we go. This S-wave scattering and the fact that it's isotropic is some good physics you get out of this problem. You may be curious, however, to wonder what happens in the case of light waves. These are Schrodinger waves. What happens with light waves? If I scatter light waves off of small particles, for example, optical radiation has a wavelength that's something like 5,000 times as big as the size of an atom. So it certainly is an example like this is low energy scattering, long wavelength scattering. So when light scatters off of an atom, is the scattering isotropic? Is an obvious question that arises here. And the answer is no, it's not. And the reason is that light waves are vector waves and not scalar waves. So the radiated wave is not an S wave, but it's rather a P wave. That's to say, it's dipole radiation, not S wave radiation. So that's how it is with light waves. To take this one step further, in the case of gravitational waves, the scattering is not S wave or P wave, it's D wave scattering. That's to say, it's quadrupole radiation. So when gravitational waves scatter, the radiation pattern produced is that of a quadrupole. This affects the dependence on radius and angle and all sorts of other things. All right. Anyway, okay, so that's enough for tonight. Are there any questions about this last part of the lecture or any part of the lecture? No questions? If not, then we'll turn it off and call it a night. I can get my finger on this.
Thank you.
Stop the recording.